Okay, so if you're going to analyze lattice experiments, I will be showing just a quick example in PROC mixed of SAS. ASREML also would certainly, its mixed model package would certainly be able to analyze these designs. GenStat I know can be used. There are some packages in R, but at least when I tried to use them, I didn't get quite the same result as I got from the methods I know in SAS. So I am not demonstrating to them today, but that may have been operator error, I'm not sure. So there are some packages that exist for these designs as well in R. And then, as I said earlier, Agribase has built-in packages for analyzing lattice designs. Okay, so I'm going to talk a little bit about the metafoam example. So just for those of you who are not familiar with metafoam, I'll give you a little background here. Basically, it's a native plant here in the Pacific Northwest. It was first produced as a crop in 1980, so it was domesticated, in the last century. The seed oil has novel long-chain fatty acids, so it gives the oil some unique properties. Very light-colored, odor-free, very stable under heat. So it's used primarily. It's used now in personal care products, but it does have other potential uses as fuel additive, lubricants, and pharmaceutical properties. Metafoam is in the Brassicales order, so it's got some similarities with the Arabidopsis and other Brassica species. So this was an experiment I did, an alpha lattice that I did in 2012, and I was very pleased with this experiment. It had very nice, good yield potential. This is a good 1,600 kg per hectare is a good yield for metafoam. We had a reasonable plot size and so on. So I was all set to use this data set for this webinar. But then when I took a closer look, I realized that I really couldn't show that I needed the lattice design in this case because it was uniform conditions and there wasn't really much benefit from using the lattice. So what the software will do is it'll make that decision for you. If there's no variation, significant variation among your incomplete blocks, then no adjustment in your means will be made. So it turned out to be a good experiment, but not a good one for demonstrating the use of lattice designs. So I went to our data from this past season. We had a little bit different situation. In this case, we had a low yield potential. We had trouble in the fall planting. Basically, it was dry. It's a winter annual crop, and it was dry as could be up to mid-October, and then the rain started and it wouldn't stop. So we didn't have really the best land preparation, and there are not that many control options for weeds in metafoam either. So we had we struggled with the weeds, and we had some gradients in the field that were related to both the hardness of the soil and the weed situation. So it turned out to be a great example for when the benefits you can attain from using lattice designs. We had 132 entries. There was 127 of our actual test cross genotypes and 5 checks I included to get up to the 132. And so I used 11 by 12 alpha lattice. We had 2 reps, just one location here in the Willamette Valley at Hislop Farm. And these plots were a little bit smaller. We didn't have as much seed generated, so we had slightly smaller plots. And as I said, quite a bit lower yield potential. Typical yields for growers here, I think the average yield is about 1,000 kg per hectare. But in our experimental plots, we typically get more like 1,500 kg per hectare. Okay, and the purpose of this particular trial, it was part of our selection for autofertility. Metafoam is an outcrossing crop, and it maintains that through various mechanisms. The anthers tend to mature before the female parts of the flower. And also, as you can see in this last little diagram here, by the time the female matures, it's up above the anthers, and the anthers have already shed the pollen. So that tends to promote outcrossing. There's also, we use commercial honeybees in the metafoam fields, but there are also a number of native pollinators that do that cross-pollinate for us. There is some potential for self-in, though. There are some related species to L. alba that are self-fertile. The flowers are perfect, it's self-compatible, and flowers close at night. So if you can reduce the difference in the height here, and you have the flowers opening and closing, there is a potential for autofertility. So this particular population I was working with was derived from some crosses to the subspecies versicolor, some self-pollinating lines that had been identified from there. The big question in my mind was whether we would get some inbreeding depression if we did succeed in increasing the autofertility. That's an open question. We know that we get inbreeding depression in subspecies alba, but we're not so sure about the versicolor. So what we did basically, we self plants in the greenhouse for 2 generations. I inherited this population from my predecessor. We took the population and self plants in the greenhouse for 2 generations without pollinators, and then we just selected for high seed number. And then we took those S2 families and put them out in an isolated nursery with honeybees to produce test cross progeny. So we want to have both the potential for autofertility in case you have very cloudy, rainy weather during the pollinating period and don't get good pollination from honeybees. But we also want to make sure we have good yield potential. So this was our isolated nursery where we were creating the test crosses. Each of these looks like a single plant, but is actually 4 to 5 sibs as part of an S2 family. So here you can see that there's a lot of variation. There's much similarity within families and variation in color and the shape of the flowers and growth habit and so on amongst the families. So the seed that we harvested from there was what I showed you in that earlier slide of the plots that we evaluated and that we're using for this example. So I got a randomization from alpha, and as you can see here, it told me the efficiency estimated would be 85%, which is acceptable. And so it gives you this, you give it some parameters, you answer a few prompts, and it gives you this plan. And in the plan, my incomplete blocks are in the rows. So, and then I have 2 replications. So this part here represents my first rep, and this represents my second rep. So just to show you, taking this first block and see how that goes out into the field, this was one of our complete reps in the field. So that first row I simply put into this particular incomplete block here, and we have 12 incomplete blocks in this particular rep, each one there. And the nice thing about these one-way designs, I mean, you can be more sophisticated and do row column designs and things like that, but these are completely flexible. I can just go out here, I can lay them out in sequence, I can serpentine. The direction doesn't matter as long as the entries that are supposed to be in a particular block stay together. It's quite flexible. I had my second rep of this actually was only 4 ranges deep and 3 sections wide, and where this one was 6 ranges deep and 2 wide. So you have lots of flexibility in how you lay these things out. And if I find that I don't have any variation among my subblocks, I can simply treat this as a complete rep and analyze it as such. Okay, so in the data set that I've given to you, I included several variables. We have, of course, measured more than this, but these are some of the ones that might be of interest. Plant height, 1,000 seed weight, oil content is very important, and seed yield. So I'm just going to show you how you would input this data here. For SAS, you would use the data step here with an input statement corresponding to each of the columns in your data set, and then so I had 132 in each of 2 reps. And you can also calculate derived variables. Oil yield is of high interest to us, which is simply the product of the seed yield and the oil percent. So that's how the data would be input. There's other options too in terms of just importing. You can import CSV files or however you want to bring them in, but this is just showing you a manual data input. And then running a mixed model analysis of yield, and I'm just going to talk today about the situation where I'm considering my entries to be fixed. I basically want to compare them and figure out which ones to select and recombine and continue on with my recurrent selection program. So I'm using ProcMix, a mixed model package, and our linear model here only includes the fixed effect, which is my genotypes, and then I have a random statement here which indicates that my complete blocks, the reps, and the blocks, the incomplete blocks that occur that are nested in each complete rep, those are my random effects. And so I can get solution for my random effects, estimates of those variance components, which I can use then to see how big or how important, say, for example, the block-to-block variation was. And then I usually have do some kind of a mean comparisons. In this case, I'm asking for everything to be compared to one of our checked varieties, Ross. And these output statements, you don't really need to have these, but if you want to have all the data put into a common file for Excel file for later use, that's a convenient way to do it. So then the output that we get, up here we have estimates for our random effects, which would be for the complete blocks and the block within reps, the incomplete blocks, and then our error term. And what you can see right here is that we have a pretty substantial variation among our blocks. And so in this case, the SAS procedure would go ahead and automatically make the adjustments to my means based on the variation that occurred among blocks. If that estimate had been 0, then there would be no adjustment made. I would just be given back the arithmetic means for my 2 reps. And down here it does do an F-test for the fixed effects as well. As you can see, I had significant variation among all of the entries for yield and for the other characteristics as well. So just to summarize here, these are the estimates for the random effects, the variances for the other characteristics as well. And you can see in this particular year, I did have substantial block-to-block rep, block-to-block variation for height. I had this estimate here is 0, so there would be no adjustment made to the means for my 1,000 seed weight because it's a pretty highly heritable trait, and there just wasn't that much variation from one block to the next. So I would simply be basing my selections on the arithmetic means in that case. Slight benefit from the lattice for an oil percentage, but not at the same extent as for yield or height, and then quite a substantial variation among my blocks for yield. So in conclusion, should we use alpha lattice designs? And I'd say yes. You don't really lose anything by using them because it's not particularly difficult or complicated. It doesn't constrain you in any way. You just have the option then to make those adjustments because you planned ahead and had done the randomization in a certain way. And it's in this situation, this is my first year oat experiments from last year. I used alpha lattices here, and they were also quite helpful. So it's when you don't have perfect experiments that you really benefit the most from using the alpha lattices. It's a good insurance policy, and it really isn't that hard to do. So I have some references here for you. And I have a separate list also in the supplemental material. And then I just want to acknowledge our funding sources, particularly the Meadowfoam Oilseed Growers Cooperative, my staff, Gary Sandstrom, Ann Corey, and our student workers. And also thanks to those who, for Dr. Frisch, for example, and Dr. Peterson in his book, and Nan Scott, who taught the experimental design class before I did. I benefited from their materials, from their training materials in developing this webinar.